There is yet another numerical scheme family which is important to know about, and this is the dissipative family. So this is a family of numerical schemes that have numerical dissipation, which means that they will not give you very accurate results at interfaces or at boundary zones between different analytes. But they will be typically faster because they can use much larger grid spacing and yet still remain non-oscillatory. So I'll give you a few examples here. This is a case that I loaded. It's again an ITP case, only that this time it has two analytes here in the middle. And it is set to 100 grid points, and currently it's set with a 6th order scheme. Let's turn the adaptive grid off for a second, save it, and start. Then this should obviously be unstable, get oscillations. Okay, stop. Let's see now what happens if we go for the 1st order. The 1st order upwind scheme is the classical scheme. It has a lot of numerical dissipation, but it should work great on this problem and solve it really fast. There you go. And that's it. The problem is solved. Now, these interfaces are very diffused compared to the real physical values. But if you're interested in the plateau values, for example, such as what is the adapted value, the Kohlrausch adapted value of the TE, then the value that you get here will be the correct value. Now, let's take a step forward and choose the slip scheme. So the slip scheme is also dissipative, but it has much less numerical dissipation. It is a 2nd order scheme, and it uses numerical dissipation only in regions where it is required. So let's save and start with this. Again, no adaptive grid yet. And you see you get similar results, but it's already starting to look better. We get a plateau value here for this blue analyte, and you see that the interfaces are slightly more sharp than they were before. Now we take the next step, stopping this, and combine the slip scheme with the adaptive grid. Maybe slower value here would do. And start. Now you see the adaptive grid working. The numerical dissipation, or the amount of smearing that you'll get, is proportional to the grid size. So once you work with the adaptive grid and you reduce the grid size at the interfaces, you're also increasing your accuracy. You're using less numerical dissipation. So now you can see this working, and you can see the interface here between the LE and the 1st analyte is much sharper than before. Everything is a little slower than before, but still very robust. You get no oscillations whatsoever, and you get the plateau values rather fast. Now you can see that this yellow analyte here, which was in peak mode in both of the previous attempts with the 1st order and the slip on a uniform grid, is now actually a plateau because the interfaces are sharp. Let's stop this here. So if you want quick and dirty solutions, meaning that you want to look at some interesting transient, or you want to extract the plateau values, but you don't really care about the shape of the interfaces, I need to stress this again. Do not trust the width of the interface that you get when you have the slip scheme. Then these kind of methods are suitable and will give you very fast and very robust results. So perhaps when you approach a problem, the best way would be to choose the slip scheme first, get a first rough solution, and then go for the next.